Okay, today's a relatively short lecture. We're just going to be talking about normalization of the wave function. So we know that the wave function is a function or a probability function, right? And it's a function of position and time, or of course velocity and time. And taking its square, or its norm squared, which is also equal to it multiplied by its conjugate, gives us a real value answer, which are the probabilities that we can find the particle at a certain point at a certain time, right? Okay, and so suppose that we have a wave function that is like this. So we have a superposition of two positions here. So it's called A and B. And then suppose we take, okay, so this is just capital psi. Suppose we take suppose we take the square of psi, or the norm of psi. Suppose we take the norm of psi. That would cause us to collapse it onto 2 points. So now it would become like this. This is A, this is B. Oh, sorry. And the problem is 0. Then a spike at A. Then a bigger spike at B. You'll notice that the local maxima are very different. The maxima at A, or maximum at A, or local maximum at A, is lower than the local maximum at B. And you notice that if we think of this as the position of the particle, right? If we think of this as the position of the particle, and this axis as the probability that it's there, you'll notice that A has a lower probability of the particle showing up there than B. So the particle is less likely to be at A than it is likely to be at B. Okay. So if we take, so this is, of course, if we take the integral of this function with respect to x, between 2 points A and B, we get our probability density between these two things. So, okay, so I'm gonna make another one. Let's call it phi 1, phi 2. Okay. And then suppose that this is my wave function squared. This is phi 2. This is phi 1. And then suppose this is my wave function. So it's just a simple Gaussian curve that's been shifted. So this integral is essentially, okay, I'm going to list it down. This integral is essentially the shaded area over here. And it gives us the actual likelihood that the particle lies between this interval. So likelihood particle lies within phi 2, phi 1. Closed. Of course, now we're talking about probabilities here, so it cannot go to past 100% probability. So over here, if B is the only thing here, right? If our wave function now is like this, or if the norm wave function is like this, we're saying that it has a 100% chance that it's going to show up at B. Or rather, its probability density at the point B, or the antiderivative of this wave function with respect to B, or evaluated at the point B, is precisely 1. Evaluated at B is 1. And likely, if we sum it all from minus infinity to positive infinity, what we're essentially saying is that, okay, we're taking the integral for all for that, how likely are we to find the particle in any space-time or in any point in space-time? And the answer to that is 100%. We will find the particle no matter where it is, in infinity or minus infinity. So, this is the most important principle when it comes to quantum mechanics, and that is that the integral from minus infinity to positive infinity of the norm of our wave function is equal to 1. So, let's write it here. Minus infinity, plus infinity. This is just like to write the dx first so that it's not, we don't have to write the parentheses and all. So dx of the norm of our wave function squared is equal to 1. Because the probability or probabilities, if you recall from your statistics, do not exceed 1. There is no 2 or there is no 1.5. But rather there is just 100%. There's no 101%, there's no 200% and stuff like that. And the problem is sometimes, especially when we're dealing with something like the infinite square well, so something like this, the infinite square well, and then suppose we have a free electron inside here, then the thing is, sometimes we end up with a wave function whose integral from minus infinity to positive infinity is 1. In fact, for this case over here, let's suppose that x here is the origin. Let's suppose x is 0. And then we want to go from x to a. Or we want to find or construct the wave function of a free electron in this square well. So if you guys would crunch in the numbers, of course you have to satisfy the equation minus h bar squared over 2m times the spatial derivative or second spatial derivative of our wave function equals I h bar times the temporal derivative of our wave function. That's just the energy operator. Okay, so it's supposed to satisfy this equation, and you notice that the function or this is a partial equation. So small psi, which we denote for partial solution, is equal to sine of n phi x over a, wherein n is any real number or integer. Maybe think of it as an integer or something. Okay, so but the problem is when we do integrate this or take its norm squared and then we take its integral, so I'm going to write here. The thing is, you'll check, if you check the integral from minus infinity to positive infinity with respect to x of the norm of this function squared is equal to a over 2. Oh no, 2 over, a over 2. You notice that that's the case here. It's a over 2, which is not 1. This isn't 1 no matter what you say. I know that it would be 1 if a is 1, but the thing is, we're not working with 1 here. We're working with a generalized thing. So what we want is a rigorous way for us to end up with 1 no matter what we choose for a. Okay? Because this would only work for one case wherein a of course is equal to 2. And our particle is located at x equals 2. But we want it such that any free electron in this square well would have this wave function. Or actually, any free electron confined in a square well with length a, okay, with length a, or any length a, would have this kind of wave function, or would have a wave function that would give us an integral of their norm to be equal to 1, or a probability density of 1. And not, some fractional stuff like this. Or, and we don't want just one case. So, okay, so you notice that this function here is not the solution, not precisely the solution. So what we do is what we call normalization. So we normalize this function. And when we say normalize, we mean add a multiple here, or to modify the function algebraically such that when we do a evaluate its integral from minus infinity to plus infinity of its norm, we would get 1, as the important property here states. So, for this case, for here, to normalize this wave function here, I'm going to write it now as the final big psi version. We add a square root of 2 over a in the front. Times, okay, the sine of n pi x over a. And then now you notice that integral from minus infinity to plus infinity with respect to x of our wave function is equal to 2 over a times a over 2, which is 1. And so we have the final answer, square root of 2 over a sine n pi x over a as our wave function. Okay, so let's apply this some more and think about a person who wants to identify as a male. Okay, so or let's go with female this time. Okay, let's go with female this time. Okay, so we have an interval and a predetermined wave function, or pre-graphed wave function. So you have interval in t. Let's call it x equals 0 up to x equals b. And let's say at x equals 1/2 b, the wave function looks like this. Okay. And then it sort of cuts off at x equals b. And then so yeah, let's say that this over here is our wave function. And then now let's draw another one here. This time with our normed wave function. 1/2 b, x equals b, and then this time, this is our normed wave function. Now this is not the scale, so this here is norm of psi squared. So we notice that at point t here, at point x, no, not x, this isn't x, this is supposed to be t, sorry. T, this is t. Okay, so notice at point t equals 1/2 b, the person is likely to identify as a female, most likely. And the other parts of our, of the interval, they don't want to identify as anything else. Okay? So just at the instant 1/2 b. So what is our wave function? Okay. So there are many different solutions to our wave function that would satisfy Schrodinger's equation. So I'll write it again. Minus h bar squared over 2m of the second spatial derivative with respect to, t this time, because we're in the t axis, not the x axis, okay, of our wave function, plus, equals I h bar times the temporal derivative respect to t. Okay. Yeah, we don't really have a second dimension here, or we don't have anything with respect to t, but I'm just going to write here for reference so you guys can check it on your own. So essentially, we can think of this as the square well problem. Okay, we can think of this as the square well problem, but we have another predefined boundary condition that at this point it is precisely 1. The probability is precisely 1, or our wave function, or the input for the wave, or the output rather, of the wave function norm squared would give us 1. Or actually, the antiderivative of this wave function, the norm of the wave function, would give us 1. Or evaluated at 1/2 b would give us 1. So integral evaluated at t equals, I'm right here at the bottom, t equals 1/2 b of respect to x of the norm of our wave function squared would give us 1. And anywhere else, give us 0. Okay, so we want to just replace A with 1/2 B. So suppose the person is treated like a free electron, like a while ago, then we can just use the wave function here. You can just use solution. Use this wave function. So the square root of 2 over A sine of n by x over A. Okay, so the normalized wave function for this, or for a free electron. If we assume that the person is a free electron, okay, we have many of assumptions at the beginning. When we're trying to solve the Schrodinger equation on its own without assumptions or analytically, it becomes really complicated really fast, and we will require something called an elliptic integral. But if we make some initial stipulations, we will be able to solve this pretty nicely. We will be able to separate the variables and be able to solve it rather neatly and fast. So just substitute. So because we're assuming the person's a free electron now, we essentially don't have to do any calculations. We just have to plug B into A. Plug B equals 1/2. And that would give us the wave function at that point. So square root of 2 over P. And so this x is actually P because we're working with the variable T. Sorry. P equals 1/2 P. So that's now 1/2 B sine n pi t over over 1/2 B. And so bring this out. There. So we bring this 2 down here, okay? Or actually, yeah. We can think of this as square root of 2 over B over 2. Yeah. And then sine of n pi t over B over 2. And then remove the 2 here, extract the 2. So extract the 2, so we get the square root of 1 over B over 2 times 2 times the sine of, once again, extract this n pi t term, and then we get 1 over B over 2 n pi t, and then this will become just 4 over B, or the square root of 4 over B, sine of 1 over B over 2. So that would just be 2 over B. And since, of course, we have to put this back, it's just 2 n pi t over B. And so this is the wave function of our given person here that wants to identify as a female at t equals 1/2 B if they are treated as a free electron. So this is our final equation here. And I believe I'll leave it to you guys as an exercise to verify that indeed this, or the norm of this, norm squared, so exercise, verify that the integral from minus infinity to positive infinity with respect to x of the norm of psi, which is this one over here, is equal to 1. And that ends this swift little lecture.